Hello, welcome to another chemistry video. I've been following Brown, LeMay, Burston, and Murphy's Chemistry, the Central Science. We're in chapter 14, which is on chemical kinetics, the way concentrations move, kinetics, and change. And this particular video is on the change of concentration with time. Now, this is the A video on that because I'm just going to cover first order reactions. The next video will be on second order reactions and half-lives. So welcome to change of concentration with time. So the previous video was on the rate law. The rate law is static. So if you know the concentration, then the rate law will tell you what the rate of change of concentration is given that concentration. But time is not really part of the equation. It's more like a snapshot, as it were. And so what if we want to know how the concentration changes with time, to bring time explicitly into the equation? Well, to do that, we're going to need to use calculus. Don't fret. I'm not going to require you to know calculus in this video, and the textbook doesn't even tell you the calculus. If you want to know the calculus, hang on to the end of this video. I'll show you the calculus at the end of the video. But if you don't want to know it, I'm not listening, just turn off the tape before it gets to the calculus. So let's take a first order reaction. Now, first order reaction basically only has one molecule, one entity that is needed to know the concentration stuff. So this is a decomposition reaction, right? Dinitrogen pentoxide is decomposing into nitrogen dioxide plus oxygen, right? So the only thing you really need to know the rate of decomposition is the concentration of dinitrogen pentoxide at any particular time. It's a first order reaction because there's a hidden one there, right? If the power is not written, then it's a 1. And so it's a first order reaction. All you need to know is the concentration of dinitrogen pentoxide and the constant to know what the rate is at that concentration. But as I said, time is not part of this equation right here, right? You can find out what the rate is if you know the concentration. But you can't say, in 3 seconds, what will the rate be? You can't say, in 5 seconds, what will the rate be? So that's where what we're about to show you comes into play. Now, this formula right here is called the differential rate law. And it's of this form. For a first order reaction, it's of this form. See, the A is to the first power. So it's a first order reaction. So the rate, that is the change in concentration of A per time, equals the constant times the concentration of A. Let me remind you why that negative is there. So the change in concentration, delta concentration A, and in the previous video we learned that delta means change in. So the change in concentration of A, because it's a decomposition reaction, it's negative, right? So this delta concentration of A is a negative number. But by convention, I don't know who made these rules, someone in a faraway place a long time ago said, rates always have to be positive. So since this is negative, we put a negative in front of it to cancel it out. A negative of a negative is a positive. So by putting the negative in front, the rate ends up as a positive number, okay? So the rate equals the negative of the change in concentration of A per time, and it equals a constant for that particular temperature times the concentration of A. This is what we learned in the previous video on rate law. Now, what we want to learn in this video is what's called the integrated rate law. And the reason this differential integration, that's calculus speak. But basically, the integrated rate law, and again, I'll tell you in a minute how we got this if you want to know. If you don't want to know how we got this, just turn off the video when we get there. But this is something you can just memorize, right? You don't have to necessarily know, well, where did that come from? You don't need to know where it came from to use it. But you'll notice that there are 4 variables here, right? You have the constant, which we had here, but now we've got time, t, in the equation. Now, if I know 3 of these variables, I can solve for the other one. So if I know the constant for that rate, for the rate of reaction, if I know the constant, then and I know the initial concentration and I know the concentration at time t, then I can solve for t. If I know the time, I want to know what it's going to be in 5 seconds. I know what the initial concentration was. I know what the constant is. I want to know in 5 seconds. Then I can find out, what the concentration is at time t. And so this is a very helpful equation because it helps you know what the concentration is going to be at a particular time. Now, let's assume that you don't remember any of your pre-calculus. You don't remember any of the analytical geometry or trig that you did or algebra. Let's say you've drawn a blank. What is ln? Because I think when I was in high school, we barely ever got to the natural logarithm. Seems like that was like at the end of the semester, at the end of the year, and our brains were full and the teacher ran out of time. So what is the natural log? Well, that's what it is. ln means natural log. That's logarithm-based e. Now, let's say you don't know what any of that means. Don't worry if you don't know what that means because your calculator does. Somewhere on your calculator, if you have a scientific calculator, you may have to hit second, and maybe lnx is above a key. It's not even one of the main keys. Maybe it's written above the key, and you have to hit a button to get it to work. But if you have a scientific calculator, I guarantee you have ln, or the natural logarithm, somewhere on that calculator. So you do the So let's say that you want to find out, at what time the concentration is something. Well, then you put in, I know my initial concentration, and I know the concentration at time t. I want to find out how long it took to get there. What is t? So you're going to basically put natural logarithm, plug in this number, minus natural logarithm, plug in this number, divide by negative k, and you've got t. So your calculator knows how to do natural logarithm, even if you don't. All right. Now, what if you know you've got these three variables here? You know the natural logarithm of the initial concentration. You know k. You know t. But you're trying to figure out what the concentration is at time t. But you've got to get rid of this natural logarithm. How do I get rid of the natural logarithm so I can get the concentration at time t? Well, again, you don't have to know why, but you ever done that string thing, where you put your hand in the string and somebody's doing stuff with the string and then they pull it and your hand's outside of the string. How do you do that? How do you get rid of a natural logarithm and pull the string and it's gone? Well, the way you do that, again, you don't necessarily have to know why this is, but somewhere on your calculator there's also the letter e, and that's called the natural logarithm constant. And it's 2.718281828 and on to infinity. It's an irrational number. It never stops. But if let's say you have a button e to the x somewhere on your calculator. If you hit that and do e and then put this number in, the result is this concentration at time t. So if you put e to the natural logarithm of something, the e and the natural logarithm cancel each other out. It's like multiplying and dividing by the same number. You end up right where you started from. So if you do e to the natural logarithm of this, the e and the natural logarithm go away, and you're just left with a sub t. Okay, so I'm trying to review a little bit in case I've completely forgotten that stuff from algebra class. That's okay. There are plenty of videos too also on it. So this is a formula to know. This basically, if you don't know anything from this video, don't understand anything I'm saying, this is the formula that this video is all about. Now, there are different ways to write the formula, and you can derive them. If you know one of the versions of the formula, you can derive the others. Here's one that may or may not be helpful to you. This formula down here is the same as this. Now, if you don't remember logarithms, you might be saying, how in the world is that the same as this? Well, there's a rule with logarithms that a logarithm minus a logarithm is the same as the logarithm of the one divided by the other. So this negative with logarithms converts into division. Don't ask why. There are plenty of videos to learn why if you must know, but you don't need to know. Just know that the natural logarithm of a minus the natural logarithm of b is the same as the natural logarithm of a over b. Okay, so this is another version of this formula. Probably the most helpful version is this one. And here, all we've done is we've just added this to both sides, and so it became 0 here, and then you had plus natural logarithm of the initial concentration. Okay, so this is the most helpful version to know, actually. If you can't, I can only handle one equation for this video. This is the form that's probably most helpful. So the natural logarithm of the concentration at time t equals the negative of the constant times the time t plus the logarithm of the initial concentration. And there you have it. This is the most helpful form to know of the integrated rate law. And like I said, now you can solve for the concentration at time t. You can solve for the time at which it reaches a certain concentration. You can solve for the constant, and you can solve for the initial concentration. If you have 3 of these variables, you can solve the 4th. Okay, now, if you're done, you can leave now. But I want to say a few more things, though, just for completion's sake. First of all, notice that this has the form of a line, y equals mx plus b, where k is the slope, because m is the slope, and b is called the y-intercept. That's where the line crosses the y-axis. So the natural logarithm of the initial concentration, that's where it crosses the y-axis. And so actually, if you graph this and you get a line, you know you have a first order reaction. If you graph this and you don't get a line, you don't have a first order reaction. So in this linear form, the natural logarithm of initial concentration is the y-intercept, and then k is the slope. Negative k, actually, is the slope. One more thing. Note that with gases, you can use pressure as a proxy for concentration. We don't really talk about the concentration of gases. And so if you use pressure instead of concentration, it'll turn out to be linear with gases undergoing reactions as well. Okay, that is the non-calculus part of this video. But let me go ahead and give you the calculus part of this video as well. So I'm sorry I don't have it unfolding, so try not to look at the bottom. So this is the rate law, right? This is where we started off this video from the previous video. For a first order reaction, the rate at any time, that is the change in concentration per time, equals the constant times the concentration at that moment. Now that's average though. Let's figure out what it is instantaneously. So with calculus, you know, we move from a generic delta, which is it could be an average, to the instantaneous dA dt. So I've just put this now into calculus form. So dA dt, negative dA dt equals k concentration of A. Now, let's go ahead and rearrange it a little bit. So let's bring the negative over to this side. Let's go ahead and take the A and bring it to the bottom. And then let's take the dt and bring it up here. So now we've got it in a form that we can integrate in calculus. So let's integrate that puppy. So the integral from initial concentration to final concentration of dA over A equals negative k, this is a constant, times the integral of dt. Well, if you know calculus, you know that the integral of dt is simply t. So the right side is going to end up negative kt. And then on this side, we know that the integral of dx over x is the natural logarithm of x. That's just something you learn in integral calculus. And so it's this integral here is the natural logarithm of a from initial a to at. And so we plug in this one first, the natural logarithm of at, minus this one second, the natural logarithm of a sub aught, equals negative kt, and there you have it, quod erat demonstrandum. That's the derivative of this formula using calculus. Well, this video has been on concentration, the change in concentration as a function of time.